We are setting off on a journey fraught with dangerous notions. Eternity, the creation of all things from nothing, and dare I utter it, a word not to be thrown around with reckless abandon among those of reason, infinity. A case in point, the Library of Babel. It is a library that holds every book that has ever been written and every book that ever will be written. Now here lies the madness. Each book is filled with random strings of letters, 26 letters, commas, periods, spaces, and each book is different. But every volume in every one of these galleries has 410 pages. Each page has 40 lines. Each line has 80 letters, ex alius, that is, through nothing but chance. So, for every sensible line of straightforward statement, there are leagues and leagues and leagues of senseless jumbles and incoherencies. For example, one volume is made up in its entirety of the letters M, C, V, perversely repeated from the very first line to the last. Another is mostly filled with gibberish until you reach the next to last page when you see, oh, time, thy pyramids. It is unbearable knowledge that in some gallery, on some shelf, a precious, cogent book exists, yet remains inaccessible. And though one cannot know, my belief is the library stretches to, dare I say it, the infinite. Many say I'm mistaken, that the possible number of books does have a limit, and while that number is beyond my understanding, I am gladdened by its distant hope that, however improbable, I may one day uncover meaning.
So, we just saw something about the Library of Babel, which is an interesting image for the universe. But tonight, you're going to hear from some people who will give you a much more expansive idea of what reality is. We're going to be talking a lot about the multiverse tonight and the notion of infinity. And we're also going to address the question, what are the fundamental constituents of nature? So, how did we get to this point in scientific inquiry into reality? Let's go back about 117 years to the year 1900. What did reality consist of? What was physical reality? Well, everyone thought it was the Milky Way sitting in this otherwise infinite space. It was eternal and wasn't created, would last forever. How naive that proved to be. Because in 20 years from then, about 1920, it was discovered that the universe couldn't be static. It had to be expanding, and this could be empirically verified. You could see the galaxies pulling away from us. So if you extrapolate back in time, you get this origin to everything, the Big Bang. So now we have a completely different view of the universe. Instead of it being eternal and static, it had a finite origin in the past, and it might end in a finite future, in a big crunch, kind of like human life. You're born, it's the Big Bang. You die, it's the big crunch. That's it. So a completely different view of the universe. And this was actually exciting to some people of religious sensibility. Pope Pius XII said when the Big Bang was discovered, this is a scientific proof of creation. The Big Bang theory was confirmed in the 1960s when the echo of the Big Bang, the cosmic microwave background, was detected almost by accident. At first, the scientists thought that it was bird guano on the antenna that was causing this interference, but it turns out it's the echo of the Big Bang. So now the question is, what is this Big Bang event? By the 1970s, some guys had come along. Two of them are here, fortunately. It's really thrilling to have them here. And they came up with the theory of the Big Bang. Let's see, do we have images of the two in their 70s hair? There they are. Not bad for 70s hair. So they set out to answer the question, what is it that banged? Why did it bang? And what was going on before it banged? And they came up with a theory which is called the theory of cosmic inflation. And so now, once again, there's a radical shift in our idea of reality. First, it was a static, finite universe, the Milky Way. Then it was the Big Bang universe. It blows up out of nothing in the seeming creation event, and then goes on its merry history. According to the new theory of inflation, our universe is just, one member of this vast, perhaps infinite ensemble of universes called the multiverse. So this is where we are right now. So let me tell you who these people are. First of all, where did our universe come from? Nobody knows, but our first guest will tell you. His name is Andrei Linde. He is professor of physics at Stanford. Our next guest is professor of philosophy at Columbia. He's the Woodbridge Professor of Philosophy at Columbia. He also has a PhD in theoretical physics from Rockefeller University. There, David Albert. Our next guest is a theoretical physicist and a string theorist. She's one of the founding members of the Center for Quantum Mathematics and Physics at the University of California, Davis, Veronika Hubeny. Our next participant is a professor of emeritus of applied mathematics at the University of Cape Town, investigates cosmology, the nature of time, the emergence of complexity, George Ellis. Our next guest is a philosopher of science. He's the only non-physicist on stage, but I think if he really had to, he could probably calculate the eigenvalues of a harmonic oscillator. Barry Loewer. And finally, this is the father of inflation, the man who really first created it in 1979, professor of physics at MIT. Professor Guth is famous for saying the universe is the ultimate free lunch. But on investigation, it turns out tax and tip are not included. And you'll hear about that. So anyway, these are our guests, and let's get this thing going. We saw this thing about infinity, and we have somebody on stage, with the more conservative view of reality, which is Professor Ellis, and he believes that nothing real can have an infinite number of components. So first of all, I want to ask you, how do you know that? And second of all, are any of you people who are committed to a reality that's infinite in some respect, like the multiverse, going to take issue with that? So how do you defend that? How do you know that?
I'll take a double stand on this. First, for me, it's a philosophical principle, and philosophical principles underlie what we do in science. And I'm going with David Hilbert, who said the infinity never occurs in physical reality, and that's because infinity is beyond what we can ever attain. It doesn't matter how many things you've done, how much stuff you've counted, how far you've gone, you haven't taken the first step on the road to infinity. And I think people forget that when they talk about infinity in loose ways. But more specifically, if you claim there's an infinite number of anything in the universe, galaxies, people or something, it's scientifically unprovable, because firstly, you can't see them, but secondly, if you could see them, you could never prove they were infinite, because no matter how many 100,000 million you have proved, you haven't taken the first step on the way to proving there's infinite. Now, I believe a scientific statement should be provable, so I think any statement about science that involves the word infinity is not provable, therefore it's not science.
What if space were infinite and it were uniform, and there were galaxies uniformly distributed throughout space? Are you saying that's metaphysically impossible?
Yeah.
Surely someone's going to object to that.
That was a what-if statement. So what-if statement, that might be true, but we can see up to 42 billion light years away. We can't see anything further. So you may say it's infinite. I may say it isn't. It closes up on itself in a finite radius. Or I can say that it's bounded by a singularity at a finite distance. You can't prove you're right. I can't prove I'm right. You can say anything you like. I can say anything I like.
Right. By the way, that's a very controversial statement, because there are many cosmologists now who believe that our part of the universe is infinite, it's flat, and it's uniformly filled with matter, including Brian Greene, I think, who's the father of this whole thing. But we have two proponents of the multiverse here. Surely you're going to take issue with this rather metaphysical claim that he's making, or maybe not.
Not necessarily.
Thank you.
Oh, okay. Go ahead, Alan.
I think I'd like to make an important distinction between what we view as space and what we view as time.
Yep.
Space, I think we have no way of knowing directly whether it's infinite or not. As you say, we can only see a certain distance and only speculate beyond that. Same thing is true about time, except for time evolution, we kind of have a theory, the Schrodinger equation of quantum mechanics. And quantum mechanics does not seem to have any natural way of ending time. Therefore, I think the reasonable assumption to pursue is that time is infinite.
But let me make a correction. The statement isn't that time is... The correct statement is not that time is infinite. The correct statement is time will be infinite in the far future, which we will never reach. Because no matter how far time has gone, you haven't reached the far future where it is infinite. So it's always in the future. So it isn't true that it is infinite.
Well, I don't think distinction has any real importance to us. I mean, space-time exists. We talk about space-time. And if we know it will exist, that's as good as... I don't know what the tense now means in the context of a space-time picture
We need a philosopher.
of reality.
We need a philosopher.
Like,
Barry, you want to go first?
Yeah, just one remark from philosophy is that Aristotle, that guy a long time ago, made a distinction between the actual infinite and the potential infinite. I think George's view is that there's maybe a potential infinity, and there's no boundary. Alan's view might be there's an actual infinite. As far as I can see, there's nothing contradictory about space or time actually being infinite. We know there are models in mathematics in which are consistent, in which there are actually infinitely many abstract entities, at any rate, numbers. Whether any scientific theory needs to posit the existence of an actual infinite is an open question, I think.
I would like to add one important statement that I didn't quite get to, which is that given what we call in physics Coleman-Delucia tunneling, technical word, if you have an infinity of time, you automatically get an infinity of space coming along with it. Space and time are more or less interchangeable in the context of general relativity.
I can pick up on that. I mean, science is full of claims. You know, current science is committed to all kinds of claims about what sorts of laws things are obeying in the centers of distant stars that we're never going to be able to witness. But we take it to be a natural extrapolation of things that we take ourselves to have good reason for believing. So the observation, which is surely true, that there's never going to be a direct empirical proof that the world is infinite or that the world is finite, it doesn't seem to me to be equivalent to a claim like we couldn't imagine ourselves having what we take to be good scientific reasons for supposing that the world is infinite or finite in this or that respect. Barry just mentioned one. You know, we have the Schrodinger equation. You know, we have all sorts of good empirical reasons for having faith in the Schrodinger equation, and the Schrodinger equation doesn't present us with a natural opportunity for the time parameter to come to an end. So it seems like a plausible thing to say that it's infinite. You're absolutely right in pointing out that that's going to be one among, you know, uncountable numbers of claims about the world that our science is committed to, which we're never going to be able to directly, empirically confirm or refute. You seem to be equating that with a claim that we couldn't have anything that counts as a good scientific reason to believe one way or another about such claims, and I guess I don't see how that follows.
And Andrei, you are the father of the theory of eternal inflation, and eternity has a kind of intimate relationship to infinity. Give us your take on this, and make it funny.
I can take infinitely large amount of time for that, but I probably will be stopped. And that actually is similar to what actually happens in our universe, most probably now. Right now, our universe tends to be, well, at least started about 5 billion years ago, exponentially expanding. And if this continues, then our part of the universe eventually will become empty. And we will find ourselves in something which is called de Sitter space. And de Sitter space has largest distance from which we can ever get any information. And this is called de Sitter horizon. So the whole universe, the whole de Sitter universe, may be infinite, but only part of it will be accessible to us. So in a sense, you'll say, OK, so what is then the multiverse if you have just a finite patch of everything to explore? On the other hand, if we study it a little bit deeper and study what happens in string theory, for example. In string theory, a lot of different vacuum states. And our vacuum state may decay in the future. And when it decays, our horizon may expand and become infinite. Or we may all collapse and die instantly. So there are some possibilities which right now we cannot even fully foresee. All of this picture of the universe didn't exist in the sense which we perceive it right now. It didn't exist about 35 years ago. So to come and say, I would forbid this picture being discussed because it's against my general principle, this would probably be, I would warn us against following the lead of those who want to forbid us something. But I don't think that George wants to forbid. He wants to put a question mark here. Be careful, because there is something which should be taken into account seriously. And I absolutely agree with this position.
And I particularly want to put a question mark against statements coming out in the popular journals saying, how far away is your next self? And I just think to talk about yourself having infinite replications is kind of really stretching beyond.
Right. In this notion of the universe, there are exact replicas, 10 to the 10 to the 100th, angstroms or light years, it doesn't matter that scale, away.
Be careful with words, because multiverse is used like a slogan by many. And if you try to Google the multiverse, who studies it, how the tendency grows up all the time. And then you do more careful search, who actually, dialing on Google the multiverse, it appears that most of the people who do it are from Peru. And then next position is from France. So what the hell is going on there? And then you fine-tune the search, and it appears that people in Peru playing the game Dragon Multiverse. So what kind of game do we play? And this is actually very, very simple. Just think about our own Earth, and there are many, many countries on our Earth. Each country has its own laws, okay? China, Russia, US, and then imagine that the size of the universe blows up to incredible size, and that's the main idea of inflation. So you have China so large that anybody living in China would have no idea about United States. And United States would not have any trade war with China, because it will be not infinitely, but practically infinite distance. And there would be no internet connection or, whatever. So then this is a very simple, very practical idea. And then somebody comes and say, oh, I live in a place where this set of laws, and this set of laws is unique, and other laws are impossible. And if I have water, then it's liquid water. And the captain of the ship just take the ship, and then suddenly in night, he crashes into solid water, and Titanic goes down. So the fact that we have seen something, experienced something, it does not necessarily prove that something else is not possible. And broader set of possibilities as a larger set of rules is more natural from my perspective than forbidding something beforehand.
I'm dying to bring Veronika into this, but I don't want to bring you in prematurely. Would you, as a string theorist, and of course the string theory feeds into the idea of the inflationary multiverse because it produces something called a landscape multiverse. But you have a slightly coy and cagey relationship to string theory because you see it more as a tool rather than as a real description of reality. But I'll let you talk.
That's right. I mean, I view it as a framework which allows all these possibilities, depending on what you put in. So it doesn't really bother me that the framework allows all these possibilities. And whether or not there's infinitely many of them, doesn't threaten our notion of reality and so forth. But let me put in a word for infinity in a context of can infinity be useful in physics? So far we have been talking about, is our universe infinite or something like that. And I sympathize with all that have been sort of said on stage here that if you count physical objects, let's say, then of course you can never get infinitely many of them. But it might still be mathematically useful notion in the sense that if you allow me that there can be, say, 0 number of certain types of objects, then I can just say, well, let me talk about 1 over that. Okay, that's a bit silly example, but it goes to sort of, it's meant to illustrate that there could be different descriptions of the same physical reality, and those different descriptions could be useful for various different things. And it could be that in one of these descriptions, the thing that's most natural is the 1 over what ends up being 0.
I think this is a very important point. I think just as infinity doesn't exist in physics, 0 doesn't exist in physics either, and that's what the quantum vacuum tells us. So I don't believe that...
What about 1? I could take 1 minus that.
I don't believe that between my fingers there's an infinite number, an uncountably infinite number of physically different points. And that's equivalent to saying that those points have 0 size. In fact, in the real universe, I believe that space-time must be quantized, it will have a little finite size, and then there won't be an infinite number of points between my fingers.
Great. Barry,
Yeah, I had 2 things I wanted to add to this conversation. One was about what Veronika just said in this discussion with George, and that is if you can count to infinity, if it took half as long to count the next thing as it did the previous thing, then of course that will be a series that converges to infinity. Sure, though, George thinks that that's an impossibility. The other thing that
what he's talking about, you can count to infinity. You say it takes you 1 second to say 1, a half a second to say 2, a quarter of a second to say 3, and so you run through all the numbers in 2 seconds that way.
The other thing I noticed was the different attitudes that Andrei and George have to what exists. Andrei's idea, if it's not forbidden, it's there. George's, you got to show me it's there, that it's there only if it's demonstrated to be there.
His is a philosophical position, mine's a physics position.
No, I think they're both
He looks really unhappy.
Well, given what I know about Andrei's background.
Philosophy and physics is shorthand for waste of time. So those are fighting. Andrei, you've been accused of being philosophical. Those are fighting.
I came 2 years from Russia, and one of my friends there expressed his attitude of the difference between how things work in different countries. And he said, in Russia, everything that it is not explicitly allowed is forbidden. In the United States, everything that it is not explicitly forbidden is allowed. And I much prefer this last possibility.
So I think that's really very good in politics, maybe not so good in epistemology.
Okay. So we've done infinity and eternity now, so let's move on to something. I mean, how about creation? Now, Andrei and Alan had both, years ago, had a kind of really clever creation ex nihilo scheme. And I understood it, and I thought, I don't know whether it's true or not, but it's an alternative to the God bringing the world into existence and all of that. And the idea was that out of sheer nothing, a little nugget of false vacuum could quantum tunnel into existence. Now, and by sheer nothing, they mean something very particular. It's a closed space-time of 0 radius. So it's like taking a balloon and shrinking it down to a point. And that's the closest you can get, mathematically speaking, to defining nothingness. So out of this beginning of nothing, a little nugget of false vacuum quantum tunnels into existence. And then, by the magic of inflation, this blows up into the multiverse. But now everyone has stopped believing in it. And you believe that the universe, the multiverse, didn't have an origin in a finite time in the past. It's eternal looking back into the past and eternal looking into the future. And I frankly don't understand this. Why were you wrong about saying it had a finite past in the first place? Alan, you had a mathematical proof that the universe had a finite beginning in the past. And now, what was wrong with the proof? And why have you completely changed your mind on this? And why should we believe you on global warming? If you, I'm kidding.
Well, nothing was wrong with the proof. What's wrong is your summary of the argument. The statement was never that the universe necessarily had a beginning. The statement was that if you followed the era of inflation backwards, the era of inflation had to have a beginning. That we still think is true. And it certainly also, I think you exaggerated tremendously when you said that now all of you people don't believe that the universe had a beginning. As far as I know, I'm really just speaking here for myself and Sean Carroll, who've been working together on a model of a universe that would be eternal. And in this model that Sean and I are working on, it really was originally proposed by Sean, to give credit where credit is due. We'd be living in an era where time is going forward and entropy, that is disorder, which we think of as almost a proxy for what defines the arrow of time. Disorder is growing towards the future and getting smaller towards the past. And in these models with a definite beginning, the universe would have begun at some finite time in the past with essentially zero entropy, zero disorder. And that's still a possibility. I don't mean to say that that's not possible. What appeals to Sean and me about this alternative approach has to do with a symmetry in physics, symmetry of time reversal invariance. All of the laws of physics that we know of are time reversal invariant. That is, we here can be sitting on the stage and talking and time is going forward. If there's also a quantum state where all of that is reversed and everything is happening exactly the same, but in the opposite order. The laws of physics don't care about distinctions between future and past. And when one puts in a beginning of this sort, you're putting in a distinction between the future and the past. We have a beginning in the past. The goal is to produce a picture of the universe or multiverse where nowhere does one put in anything that violates this symmetry between future and past. So the way the model works, there's an intermediate period, which you might think of as the logical starting point, where the arrow of time is not well defined. Disorder might be growing, might be shrinking, doing one thing one place, one thing a different place, just chaos, basically. But then if you follow that forward in time, there are laws that we think we understand which say that disorder will start to grow, entropy will grow, an arrow of time will develop going that way. And we also have in mind that all of this is going to be undergoing inflation, and in fact, eternal inflation. If you follow the same thing backwards in time, the same thing happens, but in the opposite order. The laws of physics, as I mentioned, don't care about t versus minus t. So if you follow it backwards in time, entropy, disorder starts to grow in that direction. Inflation happens backwards in that direction. So you have this two-headed arrow of time picture, and the beauty of that is the full system is completely time reversal invariant. Boom, same thing, back, boom. So you have a nice picture of the multiverse, which automatically contains an arrow of time, which was not put in by hand, but arises naturally just from the evolution of laws of physics that we think we already understand.
David, you're the natural person to critique this, because this is the man who coined the term the past hypothesis, which a very simple coinage, but it's really caught on. The past hypothesis, explain what the past hypothesis is.
That's, although I don't think it's in such dramatic conflict with this, usually before we were considering theories of the kind that were just described, we used to think that we needed to make a special posit to the effect that that there was a initial state of the universe where the entropy was very low. What's going on in Sean's proposal is that the idea is being floated that maybe the cosmos doesn't have anything like an equilibrium condition. That is, the cosmos, there isn't any upper bound to the entropy that the cosmos can have. So wherever you start out, entropy is going to go up from both sides of that. It doesn't matter what kind of state that is. That's still going to be a situation in which, on either side of this minimum, you have the equivalent of a past hypothesis. You're just not you're not claiming that things can't be that things can't be traced back even behind that. So this seems to me not something that contradicts the past hypothesis. It's an attempt to put something like a past hypothesis in a larger framework.
Right, you know, at the moment, there's this huge controversy over the inflationary theories in the multiverse. You know, we have the two of the creators of the theory of cosmic inflation here on stage. The third, you know, arguably the third father of the theory of inflation is Paul Steinhardt, who's the Albert Einstein Professor of Physics at Princeton, and he's now become an adversary of the theory of inflation. And in the Scientific American, I believe, there was an article published by Steinhardt and some collaborators arguing that the theory of inflation was a failed research paradigm. Tell us why there's so much suspicion about the theory of inflation among, you know, perfectly reputable physicists. Barry, Barry's a good friend of Steinhardt, so he can give the position.
I know Steinhardt and I know the authors, but I'm not a party to that because I'm not a cosmologist. But it does remind me of a famous remark that Lev Landau, the famous physicist, Russian physicist, made about cosmologists. I think the remark goes something like this: cosmologists, often in error, never in doubt.
That's good.
I think all cosmologists, you must be taught this at the very beginning.
So Barry, because you got to make that joke, that wasn't even your joke. Explain to us why.
You knew that was a joke.
Explain
Jim,
to us why they're unhappy. I mean, there are two reasons, as far as I understand it. There are intrinsic problems with the theory of inflation. In a way, it's too elastic. There are too many versions of it. There are hundreds of proposals for a theory of inflation, and they all hypothesize a field that does just what you want the field to do, and there's no empirical evidence that this field exists. And the other problem is that it implies the existence of a multiverse in which anything that can happen will happen. So how do you test the damn thing? So that's a very crude version.
I think there are three reasons. I don't think that, I think there's reasons to think that the kinds of field responsible for inflation could exist. And so I don't think that that's their objection so much. But I do think that there are objections that are interesting to philosophers that you mentioned. One is that, as I think you mentioned earlier, inflation was introduced in order to explain certain things about the initial, what were thought to be the initial conditions in the early universe, like that the universe has a very flat geometry, that the universe is very homogeneous. And these need to be put in by hand in the Big Bang account without inflation. Inflation looked as though it was giving an explanation of this, what looked like fine-tuning. But their worry is, and also Roger Penrose's worry, is that more fine-tuning is really needed to get inflation going in the first place. That's one worry. Another is that inflation is really a whole model, a big framework of theories with a lot of free parameters in them. And by changing the values of the parameters, the potential energy of the field and the curve of the field and so on, you can get it to adjust various empirical consequences. And that objection seems somewhat at odds with their other main and very interesting to a philosopher objection, and that is, if inflation is generically leads to internal inflation, the production of all of these pocket universes, and if these pocket universes can be very different, maybe even fill up the whole landscape of string theory, as I think some people think, then it looks like the theory itself is predicting that anything that can happen will happen, as Alan has been quoted as saying. And it looks as though a theory like that just can't have empirical evidence for it. And that's a really interesting issue to hash through. Maybe a little bit too in-house for here, I don't know, but it's...
Just real quick, I want to give you an idea of the different proposals for theories of inflation. Yours was the first. You used the term inflation first to refer to this cosmological theory. Then you came up with chaotic inflation, which became eternal inflation. Steinhardt was extended inflation. And then we have also extended inflation, double inflation, triple inflation, hybrid inflation, mutated hybrid inflation, tilted hybrid inflation, hyperextended inflation, and invariably supernatural inflation. And that's just that. And there are hundreds of others, not all of which have names. I'm sorry. I'm not. I'm meaning. You're looking. You're sort of coward.
Listing them too fast because there are much more.
Okay.
Okay. But what is important about them that all of them are just versions of one general principle. And this principle is that in the very beginning of the universe, for whatever reasons, and we can speculate whether it was tunneling from nothing, as Alex Vilenkin suggested, or some features of wave function of the universe, or whatever. There's a region of space, tiny, tiny region of space, filled with some special kind of matter, which is not very specific. And then the space, if you follow equations of motion, which anybody can solve, it's really, really simple, start expanding exponentially. And then after that, it produces big chunk of space, which is much bigger than people expected before. And after that, decaying field produce all matter in the universe. And it looks like science fiction. You solve equation, you see that's how it is. So that's a basic principle. After that, you start fine-tuning. What if I need to adjust some parameters of the theory to describe whatever data experimentalists are going to bring us? And what if I try to implement it in string theory, supergravity, grand unified theory? That's why many people suggested many different versions. They're based on the same principle. Now let's compare with the history of standard model of elementary particle physics describing weak, strong, and electromagnetic interactions. Just in describing weak and electromagnetic interactions require 20 parameters to adjust the theory to describe experimental data. Mass of the Higgs boson, very large, nobody could predict it. Mass of the top quark, very large, but people knew that top quark is necessary. So what is necessary to achieve is some framework and then feed the data. At the moment, there are some inflationary models which require just a single parameter to describe all inflation-related data which Planck satellite and other experiments give us. One parameter is enough. Is it complicated? I don't think so.
Look, here's something that people may be puzzled about. One hears two claims about inflation as it's practiced now. One, that there's spectacular, enormously impressive agreement between its predictions and what we see. Second, that it's a theory that predicts that everything that can happen will, okay, and will for certain. And there's prima facie an obvious puzzle about how to put these two remarks together with one another. If, you know, go back to your analogy of the Earth expanding. There are all these different countries. They have different laws. There are an infinite number of them, in fact. They have very, very different laws. Things are very different going from one country to another. Somebody's about to open his eyes and would like information from science about what he should expect to see. Okay? It seems like if you have a situation that the picture of the world is there's this enormous Earth on which there are an infinite number of places and everything describable is happening in one or another of those places, this is going to give the person exactly zero information about what he should expect to see. No. And in this case, it seems puzzling. Good. So this is, but presumably you understand the puzzlement. Yeah. And good.
Okay. So,
Alan, you want to answer this, but
yeah,
feel free to jump in at any moment.
Well, since I'm the one who keeps getting quoted, since I'm the one who keeps getting quoted saying that in the multiverse, anything that can happen will happen, an infinite number of times even, let me just clarify that sentence. If something has a probability of 10 to the minus 6, it means if you do something 5 times, it's very unlikely to happen. If you do it 10 to the 6 times, it's likely to happen once. If you do it an infinite number of times, it's likely to happen, has to happen, in fact, an infinite number of times. But the probability is still 10 to the minus 1/6. If you do only make a finite number of observations, the probability of you seeing that is very small. As I like to say, even if there is a multiverse, unfortunately, the probability of my winning the lottery tomorrow is not high. It remains small.
Good, but Alan, let me just jump in there for a second.
Okay, go ahead.
What you're saying implies that the picture comes along with some set of probabilities of this being the world that's realized or that being the world that's realized. And my understanding of the current status of the theory, in which people are looking for a so-called measure over these worlds, which would provide us with the probability you're talking about, is an element of the theory which is so far not in place, okay, which we're hoping is going to be in place and is going to give us the right probabilities, is going to identify what we see as a high probability kind of an event. Would somebody be wrong to say, oh, I see, so the hard part hasn't even begun yet, okay? All of the physics of this is going to rest in the choice of a measure. That part, that's an ocean of uncertainty into which we haven't even dipped our toes yet. Would that be a fair thing to say?
I think it would be a slight exaggeration. I mean, I should say a lot of what Dave just said is true. There is a measure problem, and I was just going to get there, honestly. I really was.
The measure problem has to do with probability. Whenever physicists talk about the measure problem, they're talking about a fiendishly difficult problem having to do with defining probabilities when you have an infinite number of possible events. And
right.
It's all physicists say, tend to skirt it. They tend, because it does seem to be all insoluble in every context in which it arises. But so the measure problem means a problem with defining probabilities. That's all.
Yeah,
go ahead.
I agree with that clarification. People who work on inflationary cosmology are aware of this measure problem. When we say it's an unsolved problem, I don't know, it's either an unsolved problem or a problem for which we have multiple solutions. Those are kind of equivalent statements, more or less. We don't yet know what the right solution is. We certainly do have proposals which define probabilities in ways which seem to be perfectly consistent with everything that we know of. So if we think of this decision of how to define a measure as an empirical decision, we do have ways which work empirically. I should also emphasize that there's no doubt that it's possible to define probabilities on infinite spaces. Mathematicians have been doing that for ages, for a century anyway. But there are many choices usually, and that's the issue here. So we do have to find the right choice, but there doesn't seem to be any problem in finding choices that are very sensible. What we still need and hope to find is a way of definitively determining what the right measure is.
Okay, let's get away from the measure problem. It's just too hard. And let's get on something simple like anti-de Sitter space, conformal field theory, duality, and the holographic principle, which you have to talk about because we haven't heard enough from you. You have two interesting takes on the fundamental nature of reality.
So in string theory, we have seen these remarkable statements, which we refer to as dualities, which is the interesting situation that the same physics is described by different theories, different mathematical languages, if you will. And so there isn't a sensible way to ask the question which one is correct. Right. They're both correct. In this particular example of duality, which is referred to as ADS-CFT duality or gauge-gravity duality, the two sides that describe the same physics are a theory of gravity, in particular string theory, living in higher dimensions, which is precisely equivalent to a theory without gravity, a so-called gauge theory or conformal field theory, living in lower dimensions. Okay. In fact, you can think of it as living on the boundary of the space-time that the gravity lives in. And, well, it is believed more generally through studying black holes that any theory of gravity has this holographic nature to it, that you can encode all the information that's happening in such a theory with a lower dimensional theory without gravity.
Which is weird and counterintuitive. If you could only see the shadows on the wall, you couldn't reconstruct everything that was going on at the cocktail party in the room, right?
With shadows, indeed, you couldn't tell enough. Neither can we tell with movies, which seem a little bit better than shadows, and yet they are supposed to be, two-dimensional representations of our three-dimensional world, because you don't see what's behind the, foreground things or stuff like that. So here in this holographic duality, we would have, clever shadows or things that actually know the entire theory. So indeed, that's very counterintuitive. You fit all this information on a lower dimensional theory, but maybe the point to make is that a theory of gravity already does not have as much room in it as you might have thought. And the reason for that is is gravity. Once you have gravity, you can collapse black holes, for example, which is a very generic type of behavior. And if you try to, say, pack in as much information as you can in a given region, say in this room, okay, now we can think, you bring your book and we can read it in that some amount of information. I bring another book. Andrei brings one more book and so forth. And we can pack this room with books. And that's still, there's no problem with that. But once we sort of try to packing so many books that we would sort of push at the limit of how much information can be packed in, gravity takes over and the whole thing will collapse into a black hole. And now we'll see that, in fact, the amount of information scales only with sort of the surface area of this room rather than with the volume. Okay, so gravity has somehow built in the structure of being describable by a lower dimensional theory. So that's called the holographic principle. Now this duality is a concrete realization of that, this so-called ADS-CFT duality. The ADS side stands for anti-de Sitter. It's a particular space-time that has a negative cosmological constant, so very different from the expanding universe that we're living in. But nevertheless, because it's a theory of gravity, it contains black holes. And in fact, we believe that black holes there behave just like the black holes that we see out in our universe. And now the miracle is that, yes, there is this other description, this lower dimensional description, that now does not have gravity, it does not have black holes, but everything that sort of is happening around us, all these black holes and stuff like that, are described in this completely different language. Yeah. It's very scrambled, but it's a same physics is happening in this.
In the bulk theory, in the higher dimensional theory, you've got a black hole. In the boundary theory, which is a complete description as well, what looks like a black hole is actually a bath of gluons and quarks. So David, being a philosopher, is concerned with reality as it is in itself, and he wants to know which is real. Are there black holes? Or maybe that's a naive question.
You're still asking me?
Yeah, I don't know. Dialogue. Yeah, I have my lunch here.
Yeah, I'm being forced to say something that I don't, that I'm not sure I believe. I mean, I guess there is, maybe here's a way to put the question. Look, physics has tons of mathematical equivalences in it. So we can talk about, say, the condition of a classical system of particles portrayed in three-dimensional space, or we can talk about it in configuration space, or we can talk about it in phase space. All of these are, in a very straightforward sense, mathematically equivalent, mappable into each other, isomorphic to each other. There is a temptation to say, in the classical case, yes, but notwithstanding these isomorphisms, the three-dimensional space is the real one. The three-dimensional space is the physical one. Is there an analogous question in the kinds of equivalences that you're talking? Well, there may be several things one could say about this. Maybe you think even in the classical case, the question doesn't make sense.
Well, I think
although most people would think it does.
I think there's a hidden assumption in this, which is who is asking. Okay, so you are asking, and you are sort of local object, and to you, talking in sort of the position space is most natural. So then that somehow singles out a preferred description, because in some sense, you're sort of providing the basis on which to ask this question.
But what does it mean? I don't understand how I'm part of this description too.
But you're a very specific one.
You're not, very specific
you're
one,
not, for example,
there's
spread out over
there's
this
an old
room
question attributed to Wittgenstein. People said to him, he said, I can't understand why the Copernican theory was counterintuitive. And people said, well, because it looks like the Earth goes. It looks like the sun goes around the Earth. And
So that
Wittgenstein.
answers your
No,
question,
but
no?
Wittgenstein reportedly said, "What would it look like if it looked like the Earth goes around the sun?"
Good.
So I take it the same question applies here. So is the claim, sure, if I prefer to describe things in three-dimensional space, of course I'll be describing them in three-dimensional space. If there's some psychological feature of me which prefers three-dimensional space, of course I'll describe them in three-dimensional space. Most people would say, and it sounds like you think the right thing to say about this is just that it's a mistake. Most people would say in classical mechanics, no, there's some metaphysically significant sense in which the physical space is three-dimensional, and in which the others are just sort of abstract mathematical representations. You think in the classical, right? Good.
I do not subscribe to
What
that.
he wants to ask is that if your brain is splashed on the wall, are you still
Right.
thinking?
Good. Exactly right.
So
Exactly
then you
right.
would be naturally describing things on the wall.
But your brain is splashed on the wall, according
So
to
maybe
you.
you stop
and
thinking
that
at that
brain
moment.
is describing
No,
things with
but
the
that
things
brain
in
is the same brain as the one that's in the three-dimensional
there you-
space.
Right, so there you go. So
What do you mean,
doing
where do
both.
I go?
It's doing both at the same time. I think this notion
Those are two
that there is-
things? Aren't they the same thing?
Good. So if they're the same thing, then it's a linguistic question, right? We have different descriptions of the same thing, and that thing is, there is one thing, but we're describing them in different languages. And now you're sort of trying to force me to say, well, isn't one preferred to the other because we somehow have this gut feeling that, yes, we're living in three dimensions.
I'm not trying to force you to say anything. But it's just a question. In the simple classical case, most people would say, indeed, this is how people are taught physics. Oh, I see what's going on. The real deal is three-dimensional space, and there are particles moving around in three-dimensional space. There are various other abstract mathematical representations which are useful in certain contexts: configuration space, phase space, so on and so forth. These are useful. There are all kinds of problems where I'm going to turn to those, but there's some sense in which I'm going to think what's really going on is the three-dimensional space with the particles moving around in it. And it's not that I'm claiming that's obviously right. It's interesting that that's what most people, even people with a physics education, would tend to say.
It's convenient, and it's convenient psychologically, but why is it crucial?
Because somebody wants to know what's the dimensionality of space. And it sounds to them...
David, what's your answer to that, by the way? You have a very counterintuitive answer.
Yeah,
What's the
that's
dimensionality?
another story.
Okay, well, just tell me how many dimensions space has.
N times the number of, the number of elementary degrees of freedom,
Yeah.
or
So
something
what's the
like.
order of magnitude? Is it about a Google?
It's really big.
Yeah. So we have 12 minutes left, and the two topics I thought were interesting. We're getting on to the soft ones. Beauty is a guide to truth in physics. That may be too, but George is interested in the limits of physics and the limits of science. And if we knew the universal wave function, could we predict that we were going to get together and have this particular conversation, say these particular things? Does it leave any room for free will? And you have a notion of top-down causation, which I'm very skeptical of, but I want to hear about it.
All right, I want to be... Free will is a difficult one, but let me make the following statement. According to the standard Big Bang picture, let's have a period of inflation. I'm happy with that. We've got the last scattering surface where matter and radiation decouple. We've got particles on the last scattering surface. The question is the following. If we knew everything about the last scattering surface to the finest detail, could we predict what is happening in this room at this moment? Could we predict physically what you have just said? My claim is absolutely not. There isn't the faintest chance that would be true. The reason is because, for many, many reasons, I'll just take two. One, there's quantum uncertainty between here and there, and I could amplify on that. The second one is that what cosmologists do is they characterize something called the transfer function, which goes from here to here. We have difficulty even explaining a black hole, dark halos, and so on. We have difficulty characterizing the distribution of galaxies. In practical terms, there's not the faintest chance. But supposing there was a chance of doing that, then you would be telling me that somehow the words you have just said were written into the last scattering surface by some demiurge, and I don't happen to believe that that could possibly have happened. So the real statement is the last scattering surface set up the conditions whereby higher level beings like you and me could come into being, where we had psychological powers in which we can argue at a psychological level, and that psychological level has real causal powers which are allowed by the physics, but they are not predicated by the physics. The physics cannot tell you what you are going to say in psychological terms because you're doing a logical argument, and the physics has no concept what that logical argument is.
And what you said is a highly heterodox point of view, and does anyone here agree with that? Does anyone here? Because it seems to violate the unitarity of quantum mechanics and...
well, I don't happen to believe quantum mechanics is unitary because I happen to believe that measurements take place. Every time a measurement takes place, it's not unitary. So I don't understand why any quantum physicist says quantum mechanics is unitary.
No. So do you think this is important because it does leave, lend an opening to a robust notion of free will?
Yeah.
Okay, and so surely this must have raised some hackles here. Well, these are excessively polite people, but they're raging inside.
I would like to get one clarification from George about what a measurement is, in your view. So were there measurements before there were people and apparatus?
Absolutely.
This is the quantum measurement problem we're getting into, which is really deep water.
The word measurement is come because people first discovered this in laboratories, but a measurement takes place when a superposition goes to an eigenfunction. That's a non-unitary process because you lose the information about the superposition and you end up with unspecific. That happens all the time, everywhere. It happened in the early universe when nuclear synthesis took place, long before there was any mind.
What is the law that determines when that happens?
We do not know. That's one of the big things. We don't know how it happens, and we have no specific characterization of when it happens. It's one of the big lacuna, the foundations of quantum mechanics.
And do you have any evidence that it happens?
Yeah, those pictures of the screen with the particles coming onto the screen, and you cannot predict where the next particle will come on. Those wonderful pictures, the particles come on one by one. Nobody can predict where the next one will come on, but eventually you put up those, it builds up to those interaction patterns in which you can predict with great fidelity what the final statistical thing will be. But you cannot predict what the next one will be, and that is the evidence for what I've just been saying.
Well, that's also
we'll agree with that, but isn't that consistent with the Everett interpretation and many other interpretations of quantum mechanics that do not invoke this mysterious collapse of the wave function?
Give me some way of experimentally showing the Everett interpretation is true. Just give me some hint.
I'm throwing the ball in your court.
Yeah, there are, I mean, so look, as Jim said, we're getting here into altogether different territory of the measurement problem in quantum mechanics, but we now have lots of ways of thinking about the measurement problem. It's too early to know, just as with choosing between inflationary theories, it's too early to know which, if any, of the ones we have now is going to turn out to be correct. But we have lots of ways of thinking about them which contradict crucial assumptions that you were making.
And are you supporting the Everett interpretation which he is putting forward?
No, I'm not. Actually, I'm a very trenchant critic of the Everett interpretation.
Okay, so
just for the sake of the audience, no one uses the term Everettian except
many worlds.
Just explain. There are three or four interpretations of quantum theory.
So there is this puzzle.
It's like multiverse, many-world interpretation.
Well, there's one of them is a multiverse interpretation. It gets very confusing.
Many worlds with the multiverse.
But if we come back to my question, I think Alan says there's zillions of other worlds out there in which we each said different things. Rather than what we actually said here. I think it is simpler, makes more sense to say that real emergence takes place in which we do have real psychological powers and in which we can make logical arguments, came to logical conclusions which lead to what we say, and I think that is what has happened. Not that there's this zillions of other possible things happening out there which we cannot prove are happening.
Okay, and I would say nobody on stage agrees with that, but yeah, go ahead, yeah.
Actually, the whole discussion brings us a little bit back to what we with Alan discussed, and that is about the measure problem, because right now we are returning to the measurement problem, which is a different problem, which is, however, very much related, because in both cases we are talking about whether there was something in the early universe which was definitely defined before anybody have seen it. Because the measure problem is what is the problem of the first event, which nobody have seen it, and then the wave function was not reduced, and stuff like that. So what is interesting about that is the measurement problem is discussed by everyone for almost 100 years. And you can rarely find people who are completely, in all details, agree about the solution of this measurement problem. And nevertheless, quantum mechanics works pretty well. Everywhere agree about that. So I think that this is very similar to what happens with inflationary cosmology, which we do. There are not so many people who absolutely agree about which probability measure in many universe interpretation of inflationary theory is better. But what more or less everybody agrees among experimentalists with whom we are discussing it, who are providing us with data. So more or less everybody agrees that if you have a given inflationary theory, it gives them predictions which they check, and the checking so far was pretty successful.
Let me take a simpler example. We've come into existence through Darwinian evolution. Now, my claim is the following. Darwinian evolution is consistent with physics, but it is not implied by physics. There is no physics textbook in which you will read a chapter on Darwinian evolution, because it isn't a physics result. It's a biology result.
Barry, do you guys understand this? No, this is your...
Well, a couple of things. I mean, one thing that's striking is that people could come away from here learning that there are two big issues in the philosophical foundations of physics that are on the table. The measurement problem, as Andrei was saying, the measurement problem, old one in the foundations of quantum mechanics, and the measure problem, a newer one. There's an important difference in the two cases. In the case of the measurement problem, there's quantum mechanics. Everyone learns, who takes physics, learns how to use it to make predictions in the experiments that they do. What they disagree with is what's really going on when measurements are being made, what the underlying reality is. George has one view, David may have another view, I may have another view. In the case of the measure problem, it's a problem that arises for a particular theory in cosmology, the theory of inflation, and it's really a question of whether or not the theory itself makes any predictions at all until the measure problem is actually solved. So these are two rather different, though both very important and interesting issues.
We have 3 minutes left. On the notion of beauty, very fuzzy notion, but great physicists like Steven Weinberg, the father of the Standard Model, says that we're now in an era where we don't have a lot of experimental data and observational data, that we've reached the limits of the, there won't be a bigger particle accelerator than the Large Hadron Collider built in the foreseeable future. We're sort of up against an empirical wall, and when that happens, physicists rely on their sense of beauty, and beauty has been a very reliable guide to truth. Weinberg said when he was a graduate student at Harvard, Paul Dirac came and said to the graduate students, don't pay attention to what your equations mean, just pay attention to how beautiful they are. And this is a kind of a weirdly mystical, lotus-eating notion, but beauty has proved to be a reliable guide to truth in the past, and now we're in a situation where theories like string theory, which were thought to be beautiful initially, are now looking rather ugly. And people would make the same claim about inflation, but I won't name them because I don't want to give offense to you. That inflation is an ugly theory.
Who said to you about string theory that it's ugly? Who did say to you that string theory is ugly?
Sheldon Glashow. He said it's like medieval. He said it's like medieval. Wait a minute, Sheldon Glashow is not.
Sheldon Glashow in '71 suggested his alternative to the standard model of electromagnetic interactions. Standard model was based on the theory, for math. SU2 cross U1, two different groups, two different coupling constants, many particles, anomalies, doesn't work, and he suggested his own beautiful O3 symmetric model, vector model, no no anomalies, everything is great, and everybody started, oh yeah, electroweak theory, Weinberg-Salam model, no, it's that, because it is not beautiful. And Shelley-Glashow model is so beautiful. And then they discovered neutral currents. And then where is Shelley-Glashow model? OK, he got his Nobel Prize. But the Weinberg-Salam model survived. So that's how it was.
And he got a character named after him on The Big Bang Theory, the TV show, right? Do you have one? No, there's no Andrei. There's a Sheldon. Anyone else have anything to say on any epigrammatic observations to make on beauty as a guide to truth? And it's just too fatuous. Yeah. Oh,
You have something.
Veronika.
Well, I would dispute. Well, first of all, I would dispute that string theory is not beautiful, but that's me. But I think okay, the word beauty has all these other meanings. I would think simplicity and internal consistency are much more descriptive. And certainly,
Weinberg said logical rigidity, and the example of that was general relativity. If you alter it a little bit, it crashes. Whereas string theory is very elastic.
No. Well, you might be. I mean, it has the internal consistency is very powerful tool. In fact, it's very restrictive, and I mean, it's clear to all of us that whatever we propose as a theory can't be mutually, self-inconsistent. But you might think that that's a useless thing because just about anything you propose, you can fiddle around with to make it self-consistent. But that doesn't happen. And so this takes us much further along than one might have thought. Okay. And it turns out, I mean, the physics packages itself in some nice way. And yeah, it's
the one which predicts multiverse.
Huh?
This theory predicts multiverse, so it must be beautiful.
Okay, so we've come to the end. We've heard the scientific account of the universe, and we've heard the philosophers commenting on it. So I think we should just give the last word to religion. So the religious story is, in the beginning there was nothing, and God said, "Let there be light," and there was still nothing, but now you could see it. And then I have to say thank you again, everyone.